So the first thing that I want to talk about in this video is what is the difference between an indefinite and a definite integral? So an indefinite integral looks like this. Let's say, for example, we're doing x squared. And we're taking the integral with respect to x, so we need this dx term, which we learned in the last video. So notice how there's no bounds on the integral. This means that when we take the indefinite integral of x squared, we're not concerned about the interval that we're integrating. We're looking at the x squared function as a whole, and we're integrating that whole thing. So remember the integral of x squared, that was equal to x cubed, right? We raise the exponent power by 1 and divide by 3. But this isn't where the story ends for indefinite integrals. When we take the indefinite integral of a function like x squared, we always need to add this plus c. So what this plus c means is if we have our function y equals x squared, it'll look something like this. If we integrate this function with respect to x, that basically means if we take the derivative, so if we take the derivative with respect to x of x cubed over 3 plus c, this should equal what was inside the integral, because remember, integration and differentiation are inverse operations. So this should equal x squared. So c stands for constant because when we take the indefinite integral of a function, unless we know more things about that function, more, what's the word, just more points that it passes through or more pieces of information, we don't know what this plus c is going to be. And what that means is x cubed over 3, that's going to look something like this on a graph, right? But we don't know what the y-intercept is. So it could be here, it could be here, it could be here, it could be here. There's a whole line of x cubed over 3's in which if you take the derivative of them, it's going to be x squared. And that's because if we take the derivative of x cubed over 3, right? So let's take the derivative of x cubed over 3. Well, remember, this is like 1/3 x cubed. So we're taking the derivative of that. And so this is going to be 1/3 times, we're going to bring the 3 out front, so it's going to be times 3 times x squared. So 1/3 times 3 is 1, so that cancels, and we're just left with x squared. So we know that because the inverse of an integral is a derivative, except this plus c says it doesn't matter the vertical shift of the function, because if you take the derivative of a constant, it's still going to be 0. So even if this 1/3 was shifted a million units up, so let's say we did the same thing, except our function, d over dx, our function is 1/3 x cubed plus a million. So let's say it shifted a million units up. Well, the first part here would still be the same, so it would be x squared plus the derivative with respect to x of a million. Well, the derivative with respect to x of a million is 0. So it's going to be x squared plus 0, or just x squared. So notice how the derivative is still x squared, which is our original function, which was inside the integral. So the vertical shift of a function after you integrate it does not matter, because once you take the derivative of that, you get the original function back. So that's why when we take the indefinite integral of something, we always need this plus c. Because if you don't put the plus c, you're saying that you know there's no vertical shift. You know the exact y-intercept of that function, and you don't. Because we don't know like exactly where this function is unless they tell us like, f of 0 is 5. In which case you'd know you'd need a plus 5 at the end, because that would mean the y-intercept of this function was 5. Okay, so we need to know more properties of the function before we add any constants. So we just say plus c at the end, because we don't know. Okay, so that's the first major thing. Definite integrals, on the other hand, definite integrals, those aren't functions. Those are scalar, those are constant actual values of areas underneath the curve. So let's say we wanted to find the definite integral from 0 to 5 of x squared dx. So what this is doing, this isn't a function, it's a exact value of an area underneath the curve x squared from 0 to 5. So what we do is we still kind of follow the same process. We go x cubed over 3, except we add this fancy bar at the end, and we put our bounds there. So we transfer our bounds over to these bars, and what this is saying is we're going to evaluate this from 5 and 0. We're going to subtract them. So the area is going to be 5 to the 3, so 5 cubed over 3, minus 0 cubed over 3. So the area is going to be 125 over 3. So from x squared, if we went from 0 to 5, the area under this curve would be 125 over 3 units. So that's kind of cool. That's what that's what definite integrals do. Indefinite integrals, they don't find the area, they find functions for possible areas. And honestly, indefinite integrals are going to be much more common, much more useful in things like differential equations and stuff like that. But definite integrals can be helpful when we actually want to compute the area under a curve exactly. Okay. So that's the first part. Now I want to get into the actual properties of definite integrals, because indefinite integrals, they can kind of be applied the same way, but definite integrals, let's say we have the integral of some function f of x from the interval a to b. Okay, one cool property is that we can switch these bounds. So it's going to be the integral of of b now on the bottom to a of f of x dx, except we need a negative on here. And the reason for that is if we integrate this from a to b, we're going to get a positive area. But if we go the other way, if we integrate from b, from right here to a, we're kind of traversing in the opposite direction. So if we want to get the same area, we have to tack a negative onto that. So honestly, that's a property that's not super commonly used, but these next few are going to be super crucial to understand. So stay with me here. This is called the zero property of definite integrals. So the area under the curve f of x dx from the interval a to a, so some constant to some constant, is going to be 0. Because if these bounds are the same, we're essentially saying we want to find the area from this point, we can call it a, to the same point. So we're not moving in the x direction. Our change of x is 0. So no matter what the function height is, it's going to be the function height times the change in x. So function height times 0, which is going to be 0. So if our bounds aren't changing, the integral, the area underneath, is just going to be a straight line. And the area of a straight line is just 0. Okay, this next one's called the constant multiple rule. It's just saying if we have some integral from a to b of k, some constant, times f of x dx, this is going to be equal to k, that constant, times the integral from a to b of f of x dx. So this basically just means we're factoring out k. We're bringing it out to the outside. Okay, so whether the constant is inside or outside the integral, it doesn't affect the integral itself. It's going to be the same result. The next cool thing is called the sum and difference property. So if we have some integral from a to b of f of x with respect to x, or sorry, I don't need the dx here. Let's say we're adding f of x plus g of x dx. This is going to be the same as the integral from a to b of f of x dx. So this is one separate integral plus the integral from the same bounds of g of x dx. So an example might be find the integral from a to b, or no, let's do an actual number like 1 to 3 of sine x plus x squared. dx. Or instead of sine, I'll do cosine maybe. Cos x. So now you can think, okay, well, this is going to be the same as the integral from 1 to 3 of cosine x, and I can write that as a single integral adding into another integral with the same bounds of just x squared dx. Okay, so instead of writing the entire sum inside the integrand, it's called, we can separate it into two integrals that are adding together. And we can do the same thing with subtraction. These could be subtracting, and we'd have to add that subtraction sign there. And we could evaluate them separately. That is a huge one in integral calculus, so remember that one there. Okay. The next one we can do is called additivity. This is the last one I'll be going over. So let's say we had the integral from a to b of f of x dx. Okay, and we're adding the integral from b to c of f of x dx. This one isn't as common, but it's a nice one to know. So let's think about this visually. Let's say a to b, let's say this is, actually draw it a bit bigger down here. Let's say this is a and this is b. So the integral from a to b is going to be the area underneath this. The integral from b to c, let's say this point is c here, this is going to be the area underneath the curve from b to c, so from b over here to c over here. So if we want the integral from a to c, right, if we want the integral from a to c, that's going to be the same as the two added together. Because if we have this area right here, right, this area right here, and we're adding it to this area right here, that's just going to be one big area from a to c. So this is going to be the integral of f of x, the same function from a to c. So if you can recognize that the upper bound of one integral is the same as the lower bound of another, we can just make it one integral where those two bounds don't exist, and we're just taking the lower bound of the first one and the upper bound of the second one, and just completely ignoring the b in between. Okay, and this is kind of a visual representation of why that is. So those are the properties of integrals. The constant multiple rule and the additivity, the sum and difference, the zero property, those are all properties that are super useful and that are kind of essential in doing integral problems. So if you have any questions, I know this is kind of confusing stuff, please feel free to have a comment or put a comment down and I'll be happy to respond. I hope this made some sense. I hope you're kind of getting excited into entering the world of integrals because it is super exciting and interesting. So I'll see you in my next couple videos where we talk even more about integration.